everyone. It's my honor to join you here in Indonesia to share UCloud's latest work in building scalable and reliable infrastructure for AI workloads, especially in the era of foundation models and generative AI. Here's what I will cover today. First, a brief overview of UCloud, and then the key challenges in AI infrastructure, both in training and inferencing. And next, our products and the solutions to address this. And finally, our future roadmap. Let's begin. UCloud was founded in 2012 and became publicly listed in 2020. We are one of the few cloud providers that stay neutral. We do not compete in our customers' services. We provide a full range of cloud solutions from public and private to hybrid and edge, tailored to diverse enterprise needs. We always put our customer service at the center of everything we do, with 24/7 support and 90-second response time. As for now, we've built a comprehensive cloud product portfolio, serve tens of thousands of customers, and maintain a strong research and development focus. Over half of our employees are from the R&D team. On the compliance side, we are certified with multiple global-wide credentials, meeting top-tier data security standards. Here is a brief look at our journey. We were started in 2012 and began our global expansion in 2014. By 2017, we introduced our AI-based foundational service platform. In 2020, we were listed on the stock market. Most recently, we launched our AI computing solutions from the heterogeneous GPU clusters to the Commune AI platform. These milestones mark over a decade of our continuous innovation and growth. This map highlights our global service coverage, including our local data center right here in Jakarta. Our mission goes beyond just offering compute and storage. We are here to tackle full-stack AI infrastructure challenges. Let's dive into them. In an ideal training scenarios, GPUs are fully utilized, working continuously without downtime. But in reality, large clusters break down more often than we expect. Take Meta's report during Llama 3 pre-training as an example. They experienced interruptions in nearly 58.7% of the jobs. That's far more beyond what anyone would consider acceptable. But here is the important part. Only 3 incidents required manual intervention. The rest were handled automatically. This shows that failures are inevitable, but monitoring and recovery system makes the difference. So how do we think about resilience and productivity in this context? We use machine learning productivity through a concept called good put, first introduced by Google, broken into 3 components: scheduling good put, runtime good put, and program good put. Let me briefly explain each. Scheduling good put measures how often all required resources, usually GPUs, are available when needed. If jobs are waiting for resources, this measure drops. Runtime good put reflects the number of useful training steps completed over time. It depends on how fast we can recover from interruptions. That includes time since last checkpoint, time to reschedule the slides, and time to resume the training. As shown in this diagram, to minimizing these 3 delays is the key to maximizing runtime good put. And finally, program good put, or MFU, depends on how our model code uses the available compute. This is influenced by the framework level performance, kernel optimization, and the overall software step maturity. So how to improve this? Scheduling good put is quite straightforward. We need dynamic workload schedulers and standby servers like Spot instances. Runtime and program good put requires deeper engineering. We need smart checkpoint intervals that balance the overhead with the recovery time. We must use advanced parallelism like data parallel, tensor parallel, pipeline parallel, and overlap the compute, communication, and I/O to reduce the idle time. Fortunately, we've built visualization tools that help us to identify the performance bottleneck and provide actionable guidance for the optimization. Together, these practices help us to maintain a high output even in imperfect conditions, which is the reality of the large-scale training. Okay, let's take a look at the inference scenario. Just like in training, we want the GPU utilizations to be a straight line constantly at 100%. But in reality, it's much more like a bumpy curve with highs and lows according to the user traffic and workload scheduling. Also, when we hit a business peak, we want the cluster to scale instantly like a rocket, but too often it scales like a snail. So how to solve this? We've built a flexible system with multiple levels of GPU isolation. As shown in the diagram, we support multi-tenancy, where multiple tenants can share their GPU resources and clusters. Our GPU virtualization provides fine-grained GPU slicing. So even sliced GPUs can activate different NVLink topologies without suffering from the bandwidth decay. We also support the mixed load workloads scheduling, so the online services can take the priority when the demand spikes. The offline tasks are automatically scheduled into the values of the curve, filling the idle time without affecting the user-facing performance. As for the scaling issue, we developed our own cutting-edge pod scaling technology that enables rapid scale up and scale down. So when the demand surges, the cluster will respond in seconds, not in minutes. Together, this architecture helps us to maintain a high GPU utilization, fast elasticity, and the smart workload scheduling across diverse inference needs. To overcome the infrastructure complexity, we delivered streamlined integrated solutions built for simplicity. Let's take a look at Komi is our intelligent AI scheduling platform that provides machine learning team with a unified entry point to launch the distributed tasks with a single click, monitor the end-to-end training process, and resume training from checkpoints if any interruption happens, and build runtime environment directly with the notebook. The platform is named after Koming, a legendary strategist in Chinese history, similar to Gajah Mada in Indonesian culture, symbolizing wisdom and precision. Koming integrates state-of-the-art technologies such as disaggregated preview and decode architecture built for the highest inference throughput, and the reinforcement learning workflows that simplifies the multimodal interactions. Together, the result is a powerful and developer-friendly platform that simplifies both the large-scale training and the deployment. As for the IO side, we provide UCloud parallel file system, which is designed for high performance and reliability. It delivers microsecond level data access latency and top-tier terabyte read and write throughput. With UCloud container file system, we optimized the start time of a 25 gigabyte image from 15 minutes to just 20 seconds, truly enables the rapid pod scaling. Beyond the infrastructure, we also provide Lego-style AI components that for the application builder to drag and drop modules to use the fully managed orchestration if needed, and the scenario-based performance tuning. So the startup and the enterprise teams can deploy quickly without building everything from scratch. Okay, let's take a look at how we translate our capabilities into the real-world impact. Here are a few success cases where UCloud helped our customers from diverse industries to deploy their AI at scale. The first case involves our collaboration with customers in fintech, telecom, and NCPs to build their AI computing center. Through co-selling and joint operation, we delivered hybrid GPU clusters with talent isolation and 24/7 expert support. And the next case is about we helped an embodied AI customer to build their end-to-end solution from the simulation data generation to the model training and the final deployment of the brain models, vision models, and the control models. And the last case is our machine learning engineers helped our medical client to reduce costs and double efficiency without additional hiring by fine-tuning a domain-specific model. The blur score, which is usually used to evaluate the translation task, improved from 25 to over 50, reaching the near human expert quality. Our end user is quite satisfied with the final output. Okay, let's move on to the final part. As we look ahead, UCloud is focused on four strategic directions for the next wave of AI development. The first is we are expanding our global AI infrastructure footprint, which means increasing the availability of high-performance computing resources in more regions, especially the emerging markets like Southeast Asia. Our goal is to deliver low latency, scalable AI to where the demand is growing fastest. The second is we are working on scaling foundation models more efficiently, both in terms of performance and cost. That includes optimizing resource scheduling, improving training throughput, and developing tools that help teams to manage large models with minimum overhead. The third is we are enhancing our RAG workflows, both the accuracy of the retrieved content and the automation of the agentic AI pipelines. This is crucial for the enterprise-level generative AI more useful and more reliable. And lastly, we are investing on our AI-native developed tools. There are tools designed specifically for AI development, not just a refactor from the traditional DevOps. Visualize the training workflows to debugging tools for multi-node jobs. We are helping developers to move faster and smarter. Together, these initiatives shape our future for the AI infrastructure, not just powerful, but truly useful for innovators everywhere. Okay, that's my sharing today. Thank you for your time. And if you are interested in our solutions, please scan the QR code. Thank you again.